In a similar way to solving equations, we can also find intersections between two graphs. The way we do this is if we have two graphs or two functions, we can combine them to create a single function, and their intersection is where they're going to be equal at. So I'm using the same equations or the same expressions we had earlier. X times cosine x and 2x minus 12. We used these same two expressions when we tried to find a solution for this, starting at a value of 1. Now we know that what we can do is, in order to find intersections, we'll create a single function, just like we did before. I'm not going to call it h because the h is already used here. I'll call it something else like f of x, and then look for the roots. So I just have to adjust my problem that I dealt with earlier. I have x cosine x equals 2x minus 12. That's the value of x where these two functions are going to intersect. I'm going to create a single function where, as you can see, the root of this f of x will be the 0, or will be when you get out 0. When you get out 0, it'll solve this equation, which finds the x value for the intersection. Now we know now we should not have started with the number 1. The number 7 would have been much better, we saw graphically from the last example. So we're going to apply Newton's method with the number 7. And then we'll do 3 iterations and see where that gets us. Since I'm using 7 now, I have to change all of my, and using f instead of h, I have to change all of my values here. If you plug in 7, I ended up getting out a 3.2773158. When I plugged in 7 into the derivative function, I ended up getting out a negative 5.845004. Again, I've rounded to 6. You could round to different number of decimal places if you wanted to. If you only needed your answer to be accurate within 3 decimal places, it would have been just perfectly fine to round to 4 decimal places. If you want your answer to be accurate within 2 decimal places, you could have gone out an extra decimal place and just rounded to 3. In fact, let's try to be accurate within 3 decimal places. The problem doesn't say how many decimal places, so let's say we want to be accurate within 3 decimal places. So I'll round to 4 here, and once that stays consistent, I'll leave it at that. So obviously we don't get 0 out, so 7 itself is not a root. So we're going to do a first iteration of Newton's method. Now I'm going to change these things up. So I'm going to delete a bunch of this stuff in just a second. So we've done that, and I've changed up and I've deleted a bunch of stuff. So let's take a look. So 7 minus the fraction on top, we put 3.2773. On bottom, you do a negative 5.8450. I haven't calculated that yet, but we can just type that into our calculator. I ended up with about 7.5607. Again, I'm rounding that to 4 decimal places. When you plug in 7.5607 into the function, I ended up with a negative 0.9356. When I plug that into the derivative, I end up with a negative 8.9477. Oh, I'm sorry, 9488. I didn't round that. I missed the 7. So we got pretty close to 0. Let's do another iteration there. All right, so take 7.5607, subtract your fraction. Our fraction here is negative 0.9356 divided by negative 8.9488. When I did that calculation, I found that my second approximate value would be 7.4561. Just like before, we're going to plug that into our function and then plug that into the derivative. When I plug that into my function, I get negative 0.0231 when I round to 4 decimal places. When I plug in that into my derivative, I end up with negative 8.4862. Let's go ahead and do another iteration, although we can see we're getting closer to 0. So let's find our third iteration. We would take x2 minus f of x2 divided by f prime of x2. So that is 7.4561 minus this fraction. We take the function value in the numerator and the derivative value in the denominator. I end up with 7.4534. So we're kind of honing down on where this is going to be. My function value at 7.4534 is going to be a very small number. I got negative 0.000317. That's what I get. My calculator actually gave me scientific notation. I just made that into a decimal instead. And the derivative at that value is negative 8.4734. By the way, if you do a fourth iteration, if I do a fourth iteration of Newton's method, you'll see that it doesn't change very much in terms of quantity. So what I mean by that is between x3 and x4, not a lot changes. We take the value 7.4534 and subtract negative 0.0003 divided by negative 8.4734. And what we get there is the exact same thing if I round to 4 decimal places. So we can see that rounded to 4 decimal places, this is our solution. Okay, so there you go, 7.4534. If I graph that, call it F this time, and I'm looking at where the root is, Desmos rounds things to 3 decimal places, 7.453. Obviously, if we see 7.4534 if we round to 4 decimal places. But there we go. So that's how we can find an intersection. So finding an intersection of 2 graphs, we know that the intersection happens at value x. If you want to figure out what the point is, what the ordered pair is, if I plug in 7.4534 into G, so 7.4534 into G, or into H of X, we should get a value that's very similar, like 2.906 when I plug in that number into G. If I take and plug it into H, 2.906. Again, we're very close, about 2.91 or 2.906 roughly in either of those. So my point is that the intersection point is not 7.4534 comma 0, but it is 7.4534 comma 2.91. Hopefully that makes sense. I'd like you to try this. Let's find the intersection of these 2 functions. And let's use x sub 0 equals 1 as our starting point. Let's try to be accurate within 3 decimal places. So that means you can round your numbers to 4.